G'day. Today I'd like to talk about the Fibonacci numbers. You've probably heard of the Fibonacci numbers in such films as the Da Vinci Code, but today I'd like to talk about a real guy called Fibonacci who posed a problem about a pair of rabbits. This problem went like this. If a pair of rabbits takes 1 month to mature, then mates and produces a new pair the following month, that is, 1 male and 1 female, and does the same for every month after that, and their offspring do the same, how many pairs will there be after 1 year? Now, I have a diagram here on my worksheet which you can download from my website, but first I'd like to explain basically how it works on the whiteboard. Each box represents a pair. So this is our original pair, P1, but in the first month they are immature, and then in the second month they are mature. They mate, and then the following month they produce a new pair, which I'll call P2. But of course, this pair is immature. And then P1 continues here as a mature pair. Now that means if they're a mature pair, the following month they produce another new pair, which I'll call P3, which will be immature. The pair itself, the first pair, continues as a mature pair, and P2 have now become mature. So, at the end of the first month, there is 1 pair, and at the end of the second month, there is also 1 pair. At the end of the third month, there are 2 pairs, and at the end of the fourth month, 3 pairs. So far our sequence is 1, 1, 2, 3. So back to the worksheet, where in this column I've put down what I showed on the whiteboard, that after 1 month there's 1, after the second month there's 1, after the third month there's 2, after the fourth month there's 3. Now after the 5th month there's 5, and after the 6th month there's 8. I've just numbered the pairs, if that makes it easy for you to follow this progression. But what I want to do on this worksheet is what happens at the end of the 7th month. So we have a pair here which will continue. All pairs will continue. But they are a mature pair, so they produce a new pair. This pair here is immature, so they will just mature. This pair here continues and has a new pair. This pair here continues and has a new pair. This pair just matures. This pair continues and has a new pair. This pair just matures, and this pair continues and has a new pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, using the table at the bottom of the worksheet, the progression now is 1, 1, 2, 3, 5, 8, 13. Now, is there a pattern? Well, yes, there is a very easy pattern with the Fibonacci numbers. That is, that 1 plus 1 equals 2, and 1 plus 2 equals 3, and 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. And 55 plus 89 is 144. So, we've answered Fibonacci's question. At the end of the 12th month, there are 144 pairs. This sequence is infinite. So the next Fibonacci number will be f subscript n minus 1 plus f subscript n minus 2. Okay, that's it. That's the Fibonacci sequence. On page 2, I'd like to describe some features of the Fibonacci sequence. Now I'm going to do an exercise that's on page 2 of the worksheet in the column on the left-hand side. I'm going to divide a Fibonacci number by its preceding member. So say I divide 8 by 5, I get 1.6. 13 by 8, I get 1.625. 21 by 13, I get 1.615385. 34 by 21 is 1.619048. Now, these numbers seem to be approaching the same value, and indeed they are. They're approaching a value which is given the symbol phi, Greek letter. This is usually spelt P-H-I, and it rhymes with pi. Now, the real value of this number is 1.618033989, and so on. It's an irrational number. That's because its real value is root 5 plus 1 over 2. Now you can put that into your calculator and it will give you this number. But it's an irrational number because of that square root. 1 to this number, so 1 to 1.618033 and so on, is known as the golden ratio, it's known as the divine ratio, and other names besides. It's said that this is pleasing to the eye, this proportion, and the Greeks used it in their public buildings. It also appears in great paintings like the Mona Lisa, but we must consider whether this was accidental, because we're talking about a great painter, Leonardo da Vinci, and he would be using proportions in his paintings that were pleasing to the eye. I now wish to return to the worksheet where you'll see a rectangle. This rectangle is a golden rectangle. It's made up of the squares of the Fibonacci numbers. So we start with 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared plus 13 squared plus 21 squared plus 34 squared, and the next one would be 55 squared. The special thing about this rectangle is that it never loses its shape. As we've shown in our last exercise, the proportion of one Fibonacci number to the one preceding it always remains the same. So that means that this rectangle always maintains the golden ratio. One common thing for many of us in our lives is a credit card or similar card, and if you take one of these cards and place it over the rectangle, you'll get a neat fit. And that is because credit cards are made according to the proportions of the golden ratio. They're golden rectangles. On the right of the worksheet, you'll find Pascal's triangle. And among other number sets that can be found in Pascal's triangle, the Fibonacci numbers are also there if you take the diagonals. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. Just below that, you'll find another interesting fact, that the sum of two consecutive Fibonacci squares is a Fibonacci number. For instance, term 4 squared, which is 3 squared, plus term 5 squared, which is 5 squared, is 9 plus 25, which is 34, which is a Fibonacci number. We could try that again. Term 5, which we said was 5 squared, plus term 6 squared, which would be 8 squared, is 25 plus 64, that equals 89, a Fibonacci number. Lastly, Fibonacci numbers often occur in nature. I've given 3 examples here. This one is the occurrence of leaves in a tree. This is the number of petals on a flower. And this is the number of spirals in a cone. If these numbers appear in nature, you can be sure that they're optimal ones for survival and growth. You can find some good examples at this website, or you can have a look yourself and see if you can find some examples in nature.